So it's a static condition example. Okay, what does that mean? Acceleration is 0 and force is 0. All right, so that means that all the forces, the vector sum of all the forces is 0. So what's the easiest force to calculate that's acting on this thing right now?
Gravitational.
Yeah, gravitational force. Right, so I'm going to have the force of gravity acting down. Okay, so that's going to be mass times acceleration due to gravity. Okay, 120 times 9.81 is going to be 1172, 77.2. Okay, so I've got that. Now, I have two cables that are pulling diagonally against each other and against gravity on this 120 kilogram mass. How much upward force do I need to get from those two cables? Right, 1,177.2 newtons. How much of that does each cable support? 50%. So what I've got to do is draw a triangle for each cable. Okay? The vertical component for each one of these cables is going to be half of this number, which should be 58.86, right? Or sorry, 588.6. Is that right?
588.6.
Okay. If you're wondering how I did that, I kind of have half memorized what most numbers times 9.81 are, like what 5 times 9.1 is 4.905, and I can just multiply by 10. 6 is 58.86, so I'm not doing the math in my head, okay? Okay, now if I split this thing in half, that means that this is no longer 90 degrees, this is now 45 degrees. Okay, now if it's 45 degrees, that makes my life really, really easy, because I don't even have to do trig now.
Because that is the answer.
Right, because both sides of that triangle are
45 degrees. Are
equal because of the 45-degree angle. Okay, so a question like this looks challenging, but is mathematically very simple. I only have to do one thing, and that's find out what the, well, okay, two things. I got to divide the force of gravity by 2, right? So that means then that the tension in the cable here, I'm sorry, no, I have to do one more step. Okay, I know the adjacent side to the 45-degree angle. I'm looking for the tension in B. So what trig function is going to give me the hypotenuse and the adjacent side?
Or cos.
Cos. All right, so I know then that the cos of 45 degrees equals 588.6 over B, over the tension in B. Okay, so I'm just going to move B and move cos of 45 so I can solve for B. So 588.6 divided by the cos of 45. Okay, so there's 8.3 times 10 to the 2 newtons worth of tension. I don't have to put a direction on that because it's tension. It's just how tight the cable is. Okay? So what was the one thing, the first thing I had to understand in order to get started?
That acceleration and net force are both 0.
Right. That this was a static example, there was no movement, so acceleration and net force were 0. Once I understood that, then I knew that the forces down and the forces up were equal, and the horizontal components of both cables, even though I didn't need to find them, were also equal. Okay? So that comes down to breaking this question down into its vectors, which is kind of going to be more of our focus today, is looking at more like vector component related types of questions. All right? Okay. Let's see. Yeah, we did this one. okay? But I wanna see how much you remember. So I'm going to say that this 10 kilogram box has been placed on this incline where the force of friction is 35 newtons. So it's placed on the ramp, okay? What's it gonna do?
Go down.
Okay. Force of friction is 35 newtons. Calculate the acceleration of the box. So, when I place something on an incline, what does gravity try to do? Down or down the incline?
Straight down.
Straight down. Okay, so gravity does this. Okay, and in this case, gravity is 10 times 9.81, so 98.1 newtons. Okay, as soon as gravity tries to pull this thing straight down, what does the incline do?
Push it back. Like it's the normal force.
The normal force begins to act, but normal force can only act perpendicular to the surface. Like that. Okay, so I've just drawn the two forces that are acting on that box like I would any other vector quantities. I drew them tail to head. Okay, and we found out the other day that if I draw this right, okay, and I draw the resultant, that the resultant goes there, and that not by chance, the resultant is parallel to the slope, because that's the way the box is going to go. The net force on the box has to be down the ramp, okay? All right, so what did we call that force?
Force parallel.
Force parallel. Okay, so we've had an F with two parallel lines beside it. Those lines are parallel, I promise. They don't look parallel. They're supposed to. Okay, now, in this little triangle, normal force and the force of gravity are offset by the same incline as the ramp. So this angle inside is 30 degrees. So since I know the hypotenuse of that triangle and an angle within it, can I calculate F parallel? Okay, so I got to do a little bit of trick. Right? So I'm looking for the opposite side. Which trig function? Sine. I have the hypotenuse, looking for the opposite side, right? So I'm going to go that F parallel, and F parallel is always calculated this way, okay, is the sine of whatever the angle of the incline is, in this case it's 30, okay, times 98.1, which should be 49.05. Okay, everybody with me there? So now I can start doing the free body diagram. I know that the combination of normal force and gravity is going to result in a force of 49.05 newtons down the ramp. Where do I put the force of friction? Acting up the ramp, right? Because friction always acts against us. Okay. What can I calculate now?
Net force.
Right. So, I am going to calculate net force using the vector sum of all forces. Does that mean I need to include Fn and Fg?
No, because they cancel out.
Not because they canceled out, but because I already did, yeah. My resultant F parallel was the vector sum of those two, okay? Because I get this a lot. People throw Fg and Fn in there, and F parallel, and the force of friction, they get these ridiculous numbers, okay? Because they forget I already did the vector sum of those two forces. That's what F parallel is. So my net force here is F parallel plus the force of friction. Okay, one of them is up the ramp, the other is down the ramp. So F parallel then will be, or F net will be 49.05 minus 35, which should give me 14.05 down the ramp. Okay, so I've got the net force. What is the question one? Okay, so what do I have to do with that?
Manipulate into your F equals M.
Right, do F equals M times A. Okay, solve for A, take my net force, 14.05, divide by 10, okay, and I have to two significant figures, 1.4 meters per second squared down the ramp. Would you get a mark if you said down? Nope. Because down is straight down, and this thing is not accelerating through the ramp. Okay? All right. Did we still do all the same things we've done in every Newton problem? Vector sum of all forces, F equals M times A. Well, it's just how we get there. Okay? It's being able to identify the forces, and it's being able really to visualize that situation. And drawing a diagram, that's helpful, but in the end, you've got to be able to picture in your head and put something on an incline, what's it going to do and why. Okay? And that's often a tricky thing for people. Okay? But visualization is really important in physics. All right. Write this one down. This is a vector question. Okay, we said today we were going to focus on vector questions, so this is a vector question. All right, what should I do first here? Yeah, draw my free body diagram first. Okay, they're telling me it's a level frictionless floor, and then they're giving me compass direction. So that tells me I kind of have to do like the bird's eye view of this situation, where I'm looking down on it from above. Okay, because I'm not going to draw the table, because then I can't draw the forces. They would look weird. Okay, so I'm going to draw my box. Okay, and it's 50 kilograms, and it's being pulled 35 degrees north of east. So I'm just going to draw my reference line east there. Okay, and it's 150 newtons at 35 degrees. So. And then I would have force 2, which is 10 degrees south of east, 115 newtons. So that's a pretty narrow triangle. Okay, there's my free body diagram. What should I draw next?
The X and Y components of your slope.
Before I do that, I do want to do that, but I got to draw something else first.
The resultant.
I have to get, to draw the tail to head so that I can get the resultant. Okay? Because right now, what this helps me do is visualize what that box is going to do. It's going to move mostly which way? East. But it's probably going to go also a little bit north. That's what I would think is going to happen. All right? So the next thing I want to do then is draw a vector diagram of this so that I can get the resultant and know if I'm right or not. Okay, because from there, the resultant is going to represent my net force, because it'll be the vector sum of my two forces. Okay, so I'll draw my first vector here. Okay, so this was the 35 degree one, 150 newtons. So this will be X and this will be Y. Okay, and then okay, so there's my tail to head vector diagram. Okay, there's my net force. Is it what I predicted? Mostly east and a little bit north. Okay, so now I can go about doing a vector addition thing, just like I would have done in Unit 1. Okay, I gotta find my x's and find my y's. Alright, so I'll find purple x and purple y first. So purple x is gonna be the cos of 35 times 150. Okay, so 122.87 newtons east. Okay, y is going to be the sine of 35 times 150. .04 newtons north. And then I got to find red x and red y. So red x is going to be the cos of 10 degrees times 115. Okay, so 113.25 newtons east. And y will be the sine of 10 times 115. Okay, 19.97. And that'll be south. Alright, now I've got all my x's and all my y's. What do I do with them?
Your two x's together are gonna make blue x, and then your purple y subtract subtract your red y from your purple y to find blue y.
Right. Okay, so to get, sorry, I need blue. Okay, so for blue x, they're both east, so I simply add them together. So that'll be our 122.87 plus our 113.25. So 236.13 east, and the two y's are opposite, so I've got to subtract them. So purple y, 86.04 minus 19.97. It's going to give me 66.07. Okay, now what?
Now you find your angle.
Oh, before I find my angle, I could find my angle right now if I wanted to, but I usually do this other step first.
Result.
Yeah, get Pythagorean theorem here to get my net force, right? That's the two components of my net force, okay? And then from there, I'll get the angle after that. All right, so F net is going to be the square root of 236 squared plus 66 squared, obviously with all the decimals. Okay, so 245.19 newtons, and then I got to get my direction. Okay, theta is going to be tan to the minus 1 of my opposite side, which was y, so 66 divided by x, 236, obviously with all the decimals in place. All So that's telling me 15.6 degrees, which again fits pretty well with what I predicted. Right, and that's going to be north of east. One more step.
Don't you clearly state that your F net is at the 15.6 degrees north?
Only if that's what the question asks for.
But you're after acceleration.
Right.
Okay.
So what do I do next?
Calculate acceleration using F net equals mass times acceleration, which would be your 245.19 newtons divided by the 50.
Exactly. Okay, now I gotta do F net equals m times a, just like I do in every single Newton's second law question. Okay, so F net is 245.19, I'm not gonna even bother putting the vector on there, divided by the mass, which was 50 kilograms. All right, so my acceleration is gonna be, and we have how many sig digs here? 2. Okay, so we're going to have 4.9 meters per second squared at 16 degrees north of east, or at 74 degrees east of north. Okay, is it basically just a vector question? Like, if I'd have said meters and meters and calculate the total displacement, you'd have done this exactly the same with one less step. You wouldn't have calculated the acceleration at the end using F equals m times a. Okay? So this is just building on the stuff we know from Unit 1. All that changed was I'm using forces instead of displacements or velocities or whatever. Okay? All right. Does it still require us, though, to do that visualization I was talking about? I want you guys to try from this worksheet, which is on page 4. Okay, I'd like you guys to try question number 1 and question number 4. Okay, so 1 and 4. Give you a few minutes on 1 and 4. They are very much vector dependent, let's say. Okay. So for our first one, okay, tow truck's pulling a car behind it. Friction is opposing with a force of 500 newtons. All right, so we have to assume then that the road is level, okay, and that this car is moving which way? Forward. Just forwards. It might not be being pulled straight forwards, but it's only moving straight forwards. All right, so here's the car. Okay, the car is 1,500 kilograms. Okay, and we know that the cable is attached to it and pulling this way 45 degrees, and that friction is opposing. Okay, I'm sorry, this has 2,000 newtons worth of tension in it, okay, and that friction is opposing with 500 newtons. Okay, what's the acceleration of the car? So the car, we said, is moving forwards, but the cable is pulling both forwards and upwards. Why isn't the car moving upwards as well?
Because of gravity.
Right. Okay, I have to take into account that in this situation, this upward force, okay, plus this force plus normal force, this plus this adds up to
0.
right. Okay, and again, this is one of those, I have to visualize the situation so I know gravity's not playing a factor here. Okay, normal force, not a factor here. The vertical component of the cable, not a factor here. The car's moving horizontally. Okay, so that means then that I need this force, the horizontal component of the cable, and the force of friction only, because I've already eliminated some of my vectors, right? I'm doing part of the vector sum of all forces in my head. okay, and knowing I don't have to draw them all in there. Could I? Sure. Why? Okay, like it would, my vector diagram would look like this. But then gravity, and then normal force, and then friction, and yeah. That's a pain in the neck. I don't want to have to do that. Okay, like it doesn't. I don't even think I drew that right. Okay, I just want to recognize so that I don't have to do this. Okay, that I don't need all of that stuff. All right. So, how do I calculate the force horizontal? Steve?
You just divide the 2,000 newtons by 2.
Nope.
No, you would do, the cos of 45 times 2,000.
Right. Cos of 45 or sine of 45 would be the same number either way, right? Because it's a 45-degree angle. But we're going to do that because it's correct. Cos of 45 times 2,000 newtons is going to give me that force horizontal that I'm looking for. Okay, so cos of 45 times 2,000, right, is 1,414.21. Newtons. Okay, so I've got 1414.21 newtons forwards. I've got 500 backwards. What do I do? Find the net force, right? Vector sum of all forces. All right, F net 1414.21 minus 500 will give me my net force. All right, 914.21 newtons. Now what do I do?
Divided by 9.
Right, now I do F equals m times A. So we're going to have our 914.21 divided by 1,500 kilograms, okay, and we should get 0.609 meters per second squared forward. Okay. All right. So is there some vectors to do there? Okay. But again, it's about visualizing it. How many people are done 4? Okay, I'll give you a little bit more time on 4. Read it carefully. The key things here are constant velocity horizontally. Okay, so 1 and 3, okay, are the ones that we want to work on right now. So for number 1, okay, we got a frictionless incline. So it looks like this. Box is sitting on it. It's 5 kilograms. It's 15 degrees. All right. What will the acceleration of the box be? So there's no friction here. So this is just a matter of doing that internal triangle to do our vector sum of all forces. So we have Fg. Okay. We have Fn, which we won't even need to calculate. And in fact, we're not going to need to calculate Fn until we start dealing with friction and the coefficient of friction. That's the only time we'll need normal force. That's like later this week. Okay. And then we have F parallel down here. All right. This angle here is 15 degrees. So I would have to calculate the force of gravity. 5 times 9.81 is 49.05. Okay. So I can calculate F parallel. It's the opposite side. Sine of 15 times 49.05 will give me F parallel. Okay, 12.70. Okay, any other forces I need to worry about? Is that my net force then?
Yep.
It is. Okay, so I calculated net force using the vector sum of all forces. Acceleration is just going to be 12.7 over 5, which will give us 2.5 meters per second squared down the ramp, not down. Okay, it should be down the ramp. Okay, everyone all right with that one? Elliot, you can. Okay, how many people have done 3? Are we stuck, like, are we ready to go over number 3?
I'm like, 2 seconds.
2 seconds, okay. It'll take me that long to get to it.
1, 2.
What's the answer for the last?
2.5 meters per second squared down on that. Okay, I'm just gonna draw the diagram for this one. Okay, what's the key word in this question? It's constant velocity, all right? So that means the forces up the ramp and the forces down the ramp are equal. Okay, so I'm gonna have an applied force, okay, from the slaves probably, okay, pushing up on the block. And then what forces are acting down? Okay, friction and this isn't F parallel, right? And gravity acts this way. Yeah? All right, so that's my free body diagram. I got to calculate F parallel because I know what the force of friction is. It's 800 newtons. Right? If I can get F parallel, then I can get FA. So this is FG, so it's going to be 49,050 newtons. Okay, and then F normal will be over here, which I won't need, and then F parallel is right here, which I do need. All right, so if I'm going to get F parallel, same as it always is for every inclined plane, it's the sine of the angle of incline times the force of gravity, 49,050 newtons. Okay, so F parallel is 8,517 newtons. Okay. Since it's moving upwards at a constant velocity, and we've already said that the forces down have to be equal to the forces up, right? That's the only way I get a net force of 0 and get a constant velocity. So what do I do with these two numbers? I add them together, right? If I'm going to push this thing up the ramp at a constant velocity, I have to push up with a force equal to the force coming down the ramp. Okay? That will either keep it from moving or move it at a constant velocity. In this case, it already said they were moving at a constant velocity, so all I have to do is use these two forces. So if I add those two forces together, up the ramp, or up the pyramid, or whatever. Okay? Everyone all right with that? Okay, so again, like, we had to do one trig calculation and we had to add two numbers together, all right, to finish that question. So there's really not a lot here, right, in terms of math. So much of it is understanding. Okay. I'd like you to try number 9. Number 9 has to do with this diagram here. go over number 9? Why did I pick number 9? What is it like?
The lab?
Yeah, it's like the lab, exactly.
Why is the lab bigger?
I think I made it do Tuesday, didn't I? Sorry, I gotta put it on the board.
The lab is bigger.
Okay. So we've got our 2 blocks, okay, and they're set up like this. So if we're using this to make our free body diagram, we'd have a force of gravity here. This is the 6 kilogram block, so that'll be 58.86 newtons. And then we have a force of friction that is opposing with 4.0 newtons, so not very much compared to the force that's pulling on this. All right, so can I simplify that free body diagram? Definitely. All right, so we've got 10 kilograms, 58.86 newtons that way, 4 newtons this way. So my net force is 54.86 newtons. The acceleration is then going to be 54.86 divided by 10 kilograms. Okay. Sorry, what?
10.5.
10.5 kilograms. Okay, that's what wasn't gonna work out. I was looking at the answer going, that's not right. Okay, so that's gonna give us 5.2 meters per second squared. Okay, and because it says mass 1, what do I need to put on that? Down. Yeah. Okay. Now, with regards to the lab, okay, couple of tips for the analysis. When you had your track yesterday, okay, most of you, because it's what I demonstrated, set it up on one desk and one desk only. I want you to see what that may cause as the weight shifts. As your weights pull down on this end and the cart approaches this end, is this possible? Okay, I want you to think about what force that might bring into play, because once this happens, this is no longer level, it is now an inclined plane. It may or may not have happened. Okay, or you may have had a warped piece of wood. Okay, maybe it was warped like this a little bit. Okay, things to think about. What forces did it come into play? Because remember that for your analysis, you need to look at what your numbers were and determine, did you have forces, extra forces that were helping, or did you have extra forces that were hindering, and what were they? What direction did they act in? Okay, that's question 5 and question 6 in the analysis, drawing the free body diagram, okay, and explaining why you think those forces were present. But you have to look at your data to determine which ones, if, you know, is it one, is it more than one, were present, and which ones weren't. Okay, that's the tricky part. So when I mark it, I look at your data and then I go, okay, well, from what I see, this force and this force were present. Is that what you said? Okay, does that sort of make sense? So it's not so much about the math, it's about the analysis of what happened in the lab. Okay? So that's due on Tuesday, that lab report. I'll put that up on the board, but obviously it's in Google Classroom already. If you want me to look over your lab reports before you submit them, that's fine. Just pop in at nighttime or before school or lunch or whatever, and I'll have a look at them.